Hey everybody, it is the day before the exam. Let's see if we can get some people in here. Let me say hey to the 201 chat and see if we get some people. So, start 201. We are live on YouTube and can review for the exam. Let's see right here. There we go. Okay, let's see if we get some people in here. Hey, Kaya. Hey, Rachel. How you doing, Kaya? What do you want to talk about? Rachel, what do you want to talk about? Talk about a review for the exam. Need to get a haircut. Might do it today. Might have long hair. No more. Go back to normal hair, Brian. So, and I can see today out of my contacts, which is nice. I don't know what it is. They just keep slipping on my eyes. What do people want to talk about? It's your turn to talk about. I don't think we restarted Mubot. Normal hair, Brian. My hair has gone to my shoulders 3 times in my life. I mean, this is shoulders, right? Touching my shoulders. If I can do that. Touches my shoulders. That's shoulder length hair, right? Guess it's more like, I don't know. It's like a medium cut for a lot of people. It's not really long hair yet. It's like medium hair. So, but oh, it gets in my face. So I'm like, it's pretty good. Did you get a perm? I don't know if I could pull that off, Kaya. Might look pretty crazy if I did that. People be like, what happened to your hair, Brian? My hair is very, very straight. My hair is like just very, very like fine and straight. Hey, Kylie, good to see you here. We're just talking about hair today. That's the topic of the conversation. It's just hair. How long people's hair are, what haircuts they want. Just Andrew, good to see you here. What topic should we talk about? What do people want to talk about? Let's throw out 100 $. Hey, Claire, good to see you here. We got everyone now. Oh, man. Look at that. I posted the announcement and a bunch of people. For studying for 474. So the biggest thing is know every. So we'll talk about, we'll do that. We'll do talking about like the upper level classes. And 201, ask any question you have here. So this is preparing for 474. Okay. So preparing BS 474, understanding the material. Okay, let's go check it out. Can you give us example test questions? Yeah, we can do that here next. Going over Petrie's slides. Petrie's slides are amazing, so I highly suggest doing that. Can we cover some percentile stuff? Yeah, I'll do percentile stuff too. You bet. And for 474, the biggest thing is knowing what the codes do, what the codes mean, and talking about conceptually. So when you think about, because you might have the coding exam. Hey, Ronan, good to see you here. You probably have the coding exam coming up, so I would, practice your codes where you think if you have data, and you could just make some data right here. So interestingly enough, watch this. Random normal. Test grades with an 80 and a standard. Oh, we want 300 students take the test. Let's go 1,000 students take the test. The mean is going to be 75 and the standard deviation is 10. So we're going to do a 201 question here with some 474 concepts. I'm actually going to round these. Let's say we round these to 0 decimals. Does this make sense to everybody right here that these are test grades now? Does everyone see we have test grades? How's everyone doing on this? Like 201 and 474, we're putting 2 things together. You could look at this person right here, person 970. Or you know what? We could do this for all the 201 students we have, which is close to 1,500. So these are the test grades for all 1,500 students. Let's pretend. How does that sound? Those are the test grades for all 1,500 students. And let's look at the distribution right here. How would we look at the distribution? This is good review. Let me put this 201 474 review, and I'm going to do some percentile questions on this. So we'll call this portion Stat 201 reviewing the normal curve. Good to see you here, Nick. Okay, so you might be thinking if you joined into this, wait, are we doing the normal curve? Yes, we are. How would we make a graphic to view the normal curve? So we've got here data. And how are we going to turn this graphic turn this data into a graphic? What could we do to it? So don't worry about the coding language. Think about someone has histogram. Well, boom, Kai's got the answer right there. We're going to do histogram right here of the data. And so there is a histogram of the data. So take a look at this right here. What's the first thing you notice about the histogram is the what of it. So the histogram, we would want to talk about what of it. We have 3 concepts we talk about. So what are the 3 concepts when talking about a histogram? Here's the first one, here's the second one, and here's the third. So what's the first and third right there? There's the third concept. So what are the 3 concepts? Concept 1, concept 2, and concept 3. The 3 concepts when talking about a histogram should be what? Because it's univariate quantitative data. These are the notes you want to have written down, know how to talk about these. So what are the 3 concepts? Who knows? Should be thinking something, shape, center, spread. Andrew, you got it right there. Shape, center, spread. So the shape of it, the first thing is unimodal symmetric, which is normal. The center of it is going to be the mean because it's normal. And then the spread of it is going to be the what? What is the proper measure of spread for this histogram? So we said it's unimodal symmetric, and then the center is the mean, and standard deviation is the proper measure of spread. Everything is decided from shape. So let's go ahead and take a look at this data right here. Now, what if we were to ask, what percent of students are expected to score above a 85 on this test with the information that it was normally distributed with a mean of 75 and standard deviation of 10. So this is a test question now, and we'll do some percentiles on the curve here in a second. But your first question is, what percent of students are expected to score above an 85 on this test with the information that it was normally distributed with a mean of 75 and a standard deviation of 10? So I'll go ahead and start drawing this out for you right here while you think over the question. So I'm going to go over here and start drawing on the curve. What I know about this right now is I know that the mean of the distribution is 75, which is right here. And then we go up, and great job, Jesse's already got the answers, 85, and then we'd go up here to 100 is the next one, and down here to, 65 is good right there, and then we'd go down to 45 right here. So although this looks a little bit odd right here, this is 0, 1, -2, this is 1 and +2, and what we have to do right here is we have to say between 60 to 85 is what percent of data. This is the empirical rule right here, and questions will tell you to use the empirical rule. So within plus or minus 1 standard I didn't do 1 standard deviation on the low side. Sorry about that. That's a little too far. 55 or 65. And then that would be, there's 45 there. Okay. So what do we have right here? Within plus or minus 1 standard deviation is what percent of the data? Within plus or minus 1 standard deviation is what percent of the data? 68%. Great job, Hayden, right there. And then we say the remaining outside, we divide this by 2 to get 16. That's because 32 is remaining outside and 16 is remaining here. Now, what if I were to ask you, if you scored an 85, what would be your percentile? So if you scored an 85, what is your percentile? We're doing a lot of questions right here. I'll show it here in a second. If you scored an 85, what was your percentile? So we have to know what percentiles mean, and then we can use the information we just drew to find the percentile. So it is true that 16% would have scored higher than this, but what is the percentile for that? And Nick, you're on the right track because percentile means what? When we talk about percentile right here, it's the area, and great job, Hayden, right there, and Michella, oh my gosh. Michella, please tell me if I mispronounce anyone's name. This is correct right here. It would be in good to see you, Cameron. It would be the 84th percentile. Percentile is area below the point. Percentile is area below the point. So the higher percentiles are over here, and the lower percentiles are down there. So we have to know where the percentiles are at. What percentile is directly here at 75? At 75 is the what percentile. And look at the information in the problem to help you find out that answer. At 75, that is the what percentile. What is the, at 75, that is the what percentile. So in other words, what percent of data is below the mean? So it is where the median's at also, and it's the 50th percentile. Michaela, sorry, there you go. Thank you, Michaela, right there. I appreciate that. Let's throw some points. I am very bad at pronouncing stuff, so I appreciate that, Michaela. And please tell me if I ever get it wrong, and I'm going to try to work on it. There we go. So with this right here, if you scored an 85, we could find your percentile. Now, there are questions that give you pictures. And just, Kaya, if you're wondering, points were created. There you go. We like that. And so, Kaya, you would have to maybe on your test do the following. You'd have to go here to data greater than or equal to 85. There's that. And then we would go to the mean of this vector. And this would be the percent of people. And if you notice right there, it's very close to 16%. If we keep regenerating data, it's kind of close to 16. It's not perfect, but the normal curve says we should expect about 16%. And if we look at this as a percentile, we could do the amount less than, and it's very close to the 84th percentile. Theoretically, it should be the 84th percentile, but due to randomness on generated data, it might not always be the 84th percentile. But that is how you would do it in a 474 class to generate random data and show that the 80 at an 85, someone would be at the 84th percentile, at least according to random normal. And you could just go here and do a larger simulation of data, and then you'd get a much better result, which, oh, it's showing a little bit different right there. But you could increase the simulated results. So a lot of fun stuff you can do when you have, simulations you can use. Probably we should remove that. I'm gonna do one last thing. Then let's do some that look like the David M. Lane. There we go. That's much closer. I think it was my rounding on it that was causing issues. Now it's super close to 84 with that high of a simulation, and it looks a lot more normal. So let's do a few more questions right here. I'm going to bring up the David M. Lane, which a lot of times we take pictures from that for the test. So this is some Chapter 5 review still. Hey, Brooklyn, good to see you here. So a lot of people like these problems because they're really good to practice. Here we'll go to Applet questions. So this is Stat 201 Applet, or Chapter 5 Applet questions. Chapter 5 Applet questions. And put any questions you have in the chat. Let's see right here. You ready? And let's do the following. Here we go. You scored on the exam in the 96th percentile. That same exam, we'll use the same context. What was your score? Okay. So use the information on the screen. Hero of Eternity, love it. So use the same information that we used previously. And the exam had a mean of 75 and a standard deviation of 10. You scored in the 96th percentile. What was your score on the exam to 1 decimal place? You won't use the applet on the test. It'll be a lot like Canvas content. So where the Canvas content shows you a picture, and so you would get something like this right here to solve an exam question. Boom, Hayden's already got it right there. Hayden's like, I can do this, you got it. Hayden, what is the first thing we notice about this? That this is the what percentile currently. This is the what percentile currently. The more of these you do, you start to realize how to solve them and what information you're provided. So this is the 4th percentile currently. So with this being the 4th percentile, where's the 96th percentile? So take a look as we show, which they probably figured out. I think they did. Where would the 96th percentile be? Think about how the 4th percentile means 4% of data is below here. The 96th percentile would be where? Where is the 96th percentile? So I'll zoom in on this a little bit more. Where is the 96th percentile? So it means 4% is above there, right? So the 96th percentile is where the top 4% is. Well, it is more than one standard deviation above the mean. But think about this. If this is where the 4th percentile is at, the 96th, excuse me, I say 94th, 96th percentile would be where? Directly where? And here, I'll draw it this time. The 96th percentile, which is the top 4%, yeah, kind of seeing it right there. The 96th percentile is directly where? As best I can draw. Because that's the top 4%. The opposite side of the curve. So what are we being presented down here? What is that? What is the point? And you have to know what these are down here. This is called the standard normal curve. So you have to be like, okay, I'm currently being presented what? And you can tell it's the standard normal curve because of this information right here. So everything on the curve is currently what's? They are standard deviations, and the mean is 0 and standard deviation is 1. So everything on the curve is z-scores. Great job right there. Michaela and Hayden right there. So those are z-scores on the curve. So with those being z-scores, don't tell me the answer, but say to me the answer is what to the what. Like use the z-score information and then say to me, well, the answer, Brian, here we'll go over here and do the top 4%, which is that, or we could do it as the 96th percentile, which is the top 4%. There's the 96th percentile. You could say to me, Brian, your answer is what to the what? Because if you know what a z-score is via interpretation, Rachel has it right there. The answer is, go into a little more detail because I think you've got it. But the answer to the question that we are looking for is that the person would have a score that is what to the what. 1.75, 1.751 standard deviations above the means. Michaela, great job right there. That's the exact knowledge we want you to have on what a z-score means. So we take that information right here and we literally say, let's go to the mean of 75. Then let's add to it because we're going above the mean. Remember, we said we're not doing the lower one, we're doing the positive one. And we go 1.751, and then the standard deviation was 10. 10 is a nice easy number right there. So this is basically 17.5. The 1 isn't going to matter because we're rounding to 1 decimal place. And so oh my gosh, 75 plus that is equal to 92.5. There you go. That's how we obtain it. So just understanding what you're being presented is key right there. Let's do, I'm trying to come up with some more difficult ones that use the applet. Something like, we could use the same information. Once again, just make sure you know, it's all practice. It's literally when you do a whole bunch of them, you start to understand what you're seeing, like z-scores. I can come up with a ridiculous one right here. You ready? Okay, so we're going to say, nah, I don't want to make it too hard. I don't want to make like a, because then people will wonder, people will like, I don't know. It'd be like you'd have to solve the like backward and find something else to find something else. It'd be like a 3-step solve problem, which we've never come up with anything that ridiculous. And I don't want to do something more ridiculous than we've ever put on the test. Here we go right here. Let's do this one. Let's do this one. Okay. So your friend is unhappy with their score because the teacher told them they're in the 20th percentile. Use the empirical rule to say your friend probably made a little bit above a what. So we're still using the same information we used previously, still sort of 75, 95 on the 75 on the test average with a standard deviation of 10. So to say, so you'll solve here in a moment, but use the empirical rule first. The test had a mean of 75 and a standard deviation of 10. Your friend scored in the 20th percentile. Use the empirical rule to do a quick estimate to say your friend scored a little above or below a blank. Okay. Then use the graphic to find their exact score. Okay. So quickly use the empirical rule to say my friend probably scored a little bit above a what? Okay, so your friend scored in the 20th percentile. So this is going to help us out. Sometimes questions don't have you use the empirical rule. Your friend probably scored a little bit above a what? So use the empirical rule first. Now, whenever you get a graphic like this, I'd sketch it out on my sheet of paper. We'll see. I'll wait for someone to get the right answer. Little above a 65, exactly. Little above a 65. And so we'll find the exact. So that's going to help us when we solve it to be like, a little above a 65. And the reason we know this is because if we put the numbers below here, great job, everyone. These are really proud of the knowledge people have right here. It's showing me that you've definitely practiced this, and it gets easier. It's like, okay, give me all these questions. I'll do them. I'll solve them. And the reason we know this is because between here and here is 68, and then below here is 16. We're getting that because the outside area is 32, remaining out of 100. This is why I'm going to cut my hair. And so 65, someone who scores a 65 is at the what percentile? Someone who scores a 65 is at the what percentile? So someone who's right here at a 65 is at the what percentile exactly? They're at the what percentile? The 16th. Now, someone who scores a 75 is at the what percentile? You might say, how do we know that one? Someone who scores a 75 is at the what percentile? the 50th. So doesn't it make logical sense that between the 16th and the 50th percentile is the 20th percentile? So we've narrowed it down. We said, okay, our answer has to be between 65 to 75. So now we have to know what we're being presented with. What are we seeing right here on this graphic? On this graphic, we are seeing what presented to us. And great job, everyone. Like following along right here, just practicing, reading the answers, repeating them, even if you're like trying to follow along, is a great way to get the knowledge down. What are we seeing on this graphic? Like, what is this showing us? The middle 60%. So if this is the middle 60%, what are these other areas worth outside of here? Now, it is symmetric, which is the key. So we can use the same sort of tricks right here. And what is what's going to be on the outside in both spots? 20 and 20. Great job, Jesse, right there. So we go here and we say this is 20% and this is 20%. And the 20th percentile is where 20% of the data is below here. So what then do we have for this? We don't know the answer yet, but we do know the 20th percentile's what? We do know the what of the 20th percentile, which is down there, which is what we see over here. And I'll go hand. We know the what for the 20th percentile currently. And really good work. Like the Z-score. Like this is, I feel like I've got the all-stars here right now. Like people are just like destroying these questions. I'm trying to make them more difficult. So what's the answer? What's the exact answer? You could do it to 1 decimal. I think I got it. Great job, camera, right there. Ends with a 0.6. Oh, yeah. Oh, wow. Wow. Hayden, I did it wrong in my head. Good thing I looked at it. I had 76.6 and I forgot. I thought it was a mean of 85 for a moment. It is 66.6. So the reason we're getting that is because the answer is going to be negative 0.842 standard deviations below the mean. So we go right here and we go to the mean of 75. We subtract, because it's a negative z-score, 0.842, and then we times it by the standard deviation of 10, and that equals 66 point, oh, there we go. Boom. So really good work, everyone. Excellent work. These are the problems to practice or to know how to solve pretty quickly. Here we'll go over to the other one right here. I'm trying to think of like more difficult questions. Let's see. I have to think through this one. Okay, here we go. You ready? Same sort of distribution we're working with right here. What percent of students are expected to score below an 87 on the exam? It makes more sense when you draw it out, right? When you draw it out, it makes way more sense. What percent of students are expected to score below an 87 on the exam? So you can start solving it. Same distribution we've been working with the whole time. What percent of students are expected to score below an 87? So you can use my graphic. What percent of students are expected to score below an 87? So the test had a mean, you're welcome, Nick, of 75 and a standard deviation of 10. What percent of students are expected to score below a 87? Did I say 87? That should be the right one I'm looking for. Okay, so it might help us to know something about 87. What might we find about 87 that might help us understand it a little bit better? Now, the question doesn't ask you to find this first. You might already realize it by looking at everything. The z-score, right? So to find a z-score, well, tell me what the z-score is, and great job right there. Brooklyn, we're throwing some more points. We're going here to 87, which is observation minus mean over standard deviation equals to z-score. And so what is the z-score going to be? Oh my gosh. What will the z-score be? What will the z-score be? 1.2. And take a look. Does anyone have the answer to the question yet? What is the answer to the question? Who has it? Great job, Ty, right there. I think I know it. I'll write the answer down below. I've got the answer written. Oh, you have to see this. Can't solve it without that. So round it to 1 decimal. What percent of the area is expected to be below that? And the reason we know 1.2 is because that's the z-score, and these are z-scores on the curve. So go ahead and try to solve it, see what you get. What do people have? We'll do maybe 2 more of these. We switch topics. Oh, I wrote a tough one, it looks like. Write your information on the curve and see what you're looking for. That is right, Hayden. There you go. 88.5. Let's see how Hayden got that right there. Great job, Hayden. That is the right answer. So the reason we're able to do this, wrong button there, is we know that 77, we'll round it to 77, like just for niceties. That's what I did. This is 77% of the area. So what are each of these worth? So that's 77%. What are each of those worth? Because due to the law of symmetry, there's 23% remaining outside, 11.5. Hayden, great work. Like you got these down. And then we just say the area below here. So the area to the left of there is going to be that whole area. We could just subtract from 100. But does that make sense? Does everyone else follow? Great job, Nick, right there. It's all about marking the information you have. How'd you get 77%? Right down here. Good question. It says that area shaded on the curve is 77%. So the area shaded on the curve is 77%. We're able to tell the z-score from right there that's where the z-score is at. The area between here, so this is telling us between these areas is this area right here. How's that doing, Claire? Does that make sense? So that let us know 77% right there. How are you doing on that? And then the outside would be 23% remaining total. And then we divide that in half to get each other side. We could do, is there a way to solve these questions? There are. Oh my gosh. The answer on the TI would be, let me think here. It would be, I think it'd be, I've got videos on this too. It'd be normal, CDF, and you could do -999, comma 1.2 if you know that that's the z-score. Yep. And so right there, that is how to solve it right there. Normal CDF. And I think if you go in the other way to do it is, so we'll do NCDF. You could put in -999 to do all the area below. And then we're doing an 87. Then you have to put in the mean of 75 and the standard deviation of 10. Since not everyone has the TI and it's not required, we don't require you to use it. If you have been solving questions like that, you can probably do it on the test. If you feel like the test wasn't fair to you, let me know. But here's the thing. Some questions require you to use the empirical rule. So here's a big thing to know. Very important for the test. So listen in on this. Be very careful, because here we go. A question might say this. Use the 68, 95, 99, 99.7 rule to solve the question below. What do you think you should do on this question? I know I'm asking a pretty obvious thing right here, but if you see something like this right here, what do you think you should do? If you see something like that, what do you think you should do? Not that. Oh my gosh. Yep, you're going to draw it out and you're going to make sure to use those values. So a question could say something to you like, running times in a race are normally distributed with a mean of 30 minutes and a standard deviation of 3. What percent of runners are expected to take less time than 24 minutes? Round to 2 decimals. Now be careful. If you use the calculator, you would get this wrong. So what is the answer to this question right here? If you know how to do these things, this one you can do like that. Someone might put the answer. I already know the answer because I've drawn this out so many times. I've drawn this out maybe thousands of times by now because I've taught the class. Yep, Hayden got right there, 2.5. Now, if you use the calculator, I think you get 95.449. So you get like 2.3 maybe. Because the exact area is 95.449. That's the exact. And so 100 minus that divided by 2. If you use the Applet, you'll get 2.3 if you round it, which is not the empirical rule. And the reason is when we say 68, 95, 99.7, let me draw this one out and I'll show you the reason you wouldn't get the same answer. Do you think there is exactly to the decimal 95% of area between here and here? I still want you to know 95. Don't learn these other numbers that I know. But do you think to the decimal it's 95? Like to the no, it's not. It's so when we look at this right here, it's actually 95.449. But do you think it's exactly 95.449? Like we say 95. So when we go between -2 and 2, I want to do the x values right here. -2 and 2, we say 95, but Brian says 95.449. Where's my extra 9? There's my extra 9. But is it exactly 95.4499? Now I know another number. No, there's more decimals. So there's endless decimals right here as far as it'll let me show you. Can I? It's not let me show anymore. So we just say 68, 95, 99.7. But I think it's 68. Remember, on the exam, you'll see pictures just like the problems we've been doing right here. So the exam will look like Canvas content. You won't use the applet on the exam. So you will have questions, though, that will ask you to use this right here. 99.7, and don't memorize this because I don't want you to get something wrong on the test, is actually a really cool one. What do you think the next digit is for the one that is on the third standard deviation? It's actually 99.7, and check. You can go to the applet if you want. It's an easy one to memorize. Don't memorize it. Use the numbers on the exam. But what do you think the next digit is for the third one? And I think it's 2 zeros after that. 99% or 99.7, the next digit on it is actually 3, and then it's 2 zeros, I think. So if we go right here, 99.73, and then 2 zeros. Oh, and then a 2. That's easy to memorize, too. Try to come up with patterns to memorize stuff, but 99.73. It's actually 68.26, I think. There it is, 68.26, and then 95.4499, and then 99.7300. The things I do with my time. But we don't use those extra digits. We just round them to 68, 95, 99.7. You don't get a sheet of notes on the exam, though. No notes on the exam. I think you can. Can you currently view? I might even show that. Can you currently view the exam? I'll put this as a new section in the video. What you get on the exam. So I think you can view it. I'm going to put this as a new section right here. 33, 53, Stat 201. What you can bring to the exam. What you get for the exam. Okay. Log into Canvas right here. There's I don't think there's a preview, but you can go to the exam, and I think you can click it. Which problem do you want me to explain how to solve, Claire? Oh, the one we just did, maybe? I can explain the one we just did if you like. So if you go to, I can't preview it. Oh, wait. I think when you go to it, it might not let you start it, but you can see right here what you can bring. So this is all the information you can share on here. So everything, if you want to screenshot this or take a look at it later. Yeah, and then we'll do that one we just did right there. The 24-minute one. Oh, the 24-minute one? What's the 24-minute one? Bitch, can you, there's a test preview one? Is there? How do I not know about this? But definitely look at what is optional, blank sheet of paper you can bring. You can bring your own calculator. You can use the proctorial one. There is no formula sheet. Exam 2 and 3 will have one. And bring your UTID or some form of ID. It can be on your phone or whatever. Just make sure you don't have your phone open beside you for the rest of the exam. Put it over to the side. Put it away from you. I mean, like practice tests is, I think there's one. Oh, yeah. Review 1 has the Stat 201 exam or practice test. The recent one we just did. Yeah, less than 24 minutes. Let's go take a look at that here again real quick. So this problem right here, what's the first thing you would probably do with 24? So what would you do with this observation? And then what topics should we cover next? Think about what you're going to do with that observation right there. What is the first thing you would do with it? You always have to take all the information you have, start marking it down, think about what to do. Being in yourself is really good. Being by yourself is really good right there. If for some reason dog comes by, parents say, "Hey, what are you doing?" or roommates like, "Hey, what are you doing?" Not the end of the world. So solve for the z-score. Yep. Observation minus mean over standard deviation is equal to 24 minus 30 over 3, and that equals to -2. Once we hear -2, we think about the second part of the 68, 95, 99.7 rule. If we know that 95% is between here and here, then that makes these other areas worth what and what. And we are looking for the time for people taking less than it. So just be there. So what are those areas worth right there? Because if 95% is between those areas, then what are those blue areas worth? 2.5 each. And does that make sense, Claire, right there? That's where we're getting 2.5. We could do another problem off this same sort of data right here. So I'm just going to copy. Sure, why not? We're just trying to do as many of these as we can. How about, I'll give you a tough one. So here's a tougher one. It's one of those annoying ones that what percent of runners take more time than 21 minutes? Okay, put a question mark on it this time. So I can get this one pretty quickly too. Like I said, I've done a lot of these. So if you're thinking through how to work problems like this, I would first find your z-score, then draw your curve. Be very careful. A lot of people put the wrong decimals on this. We have to be very exact on our answers. This one's going to be to 2 decimal places. So what would be your answer? And make sure to use the rule right here. You don't want to use the calculator, your calculator, the TI calculator, the applets. You won't use the applet during the test. But what would be the answer to this one? So the first thing you want to do is find out the z-score for this. So we'd have here observation minus mean over standard deviation. This is the mean, which is mu. This is the standard deviation, which is sigma. This is the observed value. Somebody runs an observed value of 21 minutes. So 21 minus 30 is -9. -9 over 3 is -3. So what would be the answer to this? We're going to draw the curve down here below while you think it over. Well, that is the great job, Claire, right there. That is their z-score. So what percent of runners are expected to take more time than this? What percent of runners are expected to take more time than this? Ooh, I asked a tough one, it looks like. Stumped everybody in the class. So what percent of runners? So Amelia, good answer, Amelia. We'll throw some points for that. Good. You're on the right track. People are on the right track. Is this let me ask you this. Is this a very fast time for the race? Is that a very fast time for the race? So the race had an average of 30. Is 21 very fast? Is 21 a fast time when the average runner was running it in 30 minutes? So we'll throw some points right here. It's very fast. So the average runner was taking 30 minutes. And we are 3 standard deviations below the mean. We're down here at 21. Great job, Hayden, right there. So what we need to do, and great work, everyone. Let me throw some more points. This is where the practice comes into play. Is the first thing I would do is I would notice that this is a very what area? Because we are taking more than this time down here. We want more than. So I'd notice that this, and great job, Nick, right there. I'd notice that this is a very large area. Does that make sense? So that's a very, very large area. So we have everything but this area over here, right? So let's just call this area X for the moment. What is going to be the answer? Which, look at what Nick has and then think, well, if Brian shades everything to the right of this line, and then we have this line, and we call this area X, which we will find here in a moment, how could we solve it? Like, what would be the answer? And look at Nick's answer for some kind of clues on that. If we call that area X. Just saying it's some amount. Like, I could call it 1%. So, like, if this area was 1%, what would the blue area be? Like, just it's not 1%. Good guess, Ty. What would the blue area be over here if that area over there is 1%? Just theoretically. It's not 1%, but that's an easy thing to do. 99, yep. So it's going to be 100 minus that. So we have to find the yellow area to be like, okay, what's the other side worth? So to find the yellow area, we're going to go between here and here. And how much area is between -3 and +3? How much area is between -3 and +3? $99.7. So now outside is how much? 0.3 divided by 2, because the remaining outside. And there's the outside. What are the two ways, way number one, or we can call it way number one, or way number two to solve this? What are two ways to solve this question right here? What are two ways? Question for on the practice exam? Yeah, we can do it right here. And we've got practice exam videos for everything, but I'm happy to do some practice exam questions. What are two ways to solve this right here? And the more ways you know how to solve them, the more ways you can check your work. So we are looking for the area over here. Yep, Hayden, both ways. Great job, Hayden, right there. Yep, you could add up the areas to the right of it, or you could subtract from 100 the missing one, and 99.85 is going to be the answer. The more ways you know how to solve it, or you could do something crazy. Wouldn't suggest it by going down here, and if you know all the areas between, you could technically do the following, which would be a very long solve for it. You could go 2.35, 13.5, 34, 34, 13.5, and 2.35, and do that right there. Oh, and 0.15. Or you could just do, if you know 0.15 is there, you could just subtract that area off of it. But you could add up all those areas, which I would not suggest doing that long solve right there. But there's many ways to solve these questions. Let's do practice question number 4 on the exam, practice exam. And yep, there are. And so if you're wondering, and we will definitely do it here, I like to give another explanation to this, but let's put this down in the video. 23, 23. Stat 201. Practice exam question 4. And there are, Emma, good to see you here. There are practice exam reviews for each question. Where's my videos? Show up videos. Sometimes this page acts weird. Is it going to show up? Terry, you better not have done something to the site. No. So I think these videos are showing up for everyone else. Let me know if they're not showing up for you. I think everything should be good on covered right here. So it should eventually load. One more try here. Gonna load my videos. It's weird. I don't know if it's the WordPress site hosting or sometimes, or maybe everyone's going here and it's having trouble loading. Like UT servers are not used to so many people going to check it out. But I could post the link to the reviews. But they are on here if the videos ever load. That's really weird. I don't like that. So let's go here to number 4. Number 4. Okay. So professional goalie hockey times have a average of this and a standard deviation of this. We want the 75th percentile. So when we do the 75th percentile, the first thing I would do is start marking these curves. So we need to figure out the 75th percentile and where it's at. So this is how exam questions might look for you right here. And when we do the 75th percentile, we need to know what all these curves are showing us, right? So where would the 75th percentile be? Does anyone know where the 75th percentile would be on the curve? To the right or to the left? And we did some questions like this earlier. Would the 75th percentile be over here? Or would it be over here on the curve? Be to the right because it's a higher percentile. So the 75th percentile is to the right on the curve. And we need to figure out which one of these works. Now, this graphic right here has something very interesting about it. How would you describe what you are currently seeing on this graphic? You are seeing the what percent on the curve. How are you describing how would you describe what you're currently seeing? The what percent on the curve? The bottom 25%, right? So if we want the top 25%, where would the top 25% be? So instead of us getting the bottom 25%, where would the top 25% be? The top 25% would be where? The mirror image, right? So we're going to do something on this question to make it a little bit easier of a solve. So we're just trying to find the 75th percentile, which is where the top 25% is at. And I like to do this question this way because it makes it way easier to solve and you don't have to worry about decimals. So this is still the same question. Where is the top 75%, or where's the 75th percentile, i.e. the top 25%? But watch this. If this is where the 25th percentile is, can anyone answer where the 75th percentile is? So we're going to use this number right here to find the answer and take a moment right now to find the 75th percentile using the information given. And then we'll show how we solve this. But now the problem is way easier. Nick, that is right. So now you can do this problem in your head probably. Nick is showing the theory, and then we're going to show what Nick found and show why this works. So go ahead and solve this right here without the decimals. The decimals just make it more of carrying decimals problem. So what's the answer going to be? People are showing the answer. So what will the answer be? Yep, 157-ish, and that's because we took off some decimals. So what we know is that the 25th and the 75th percentile have a symmetric distance from the mean. So how far below the mean is this? 7. How far above the mean would the 75th percentile be? Well, it's going to be right over here, and it's going to be 7 above the mean. So if this is 7 below, this would be 7 above. So this is just taking off the decimals. We could do it more exactly right here. The answer is 157. But if we want to find out more exactly, we could just do the same process of find out what the exact distance is, which is 150 minus 143.258. So now we just add this to 150, and there's the answer right there. So what's really great about this is we could have done this in the applet, but it gave us the pictures basically. So we would just enter in the mean and standard deviation, and there's the answer, and there's our answer. It's just that there's an extra decimal or two carried right there, but we were able to solve it. Does that make sense right there to the person who asked the question? This is how we can solve it, knowing the rule of symmetry right here, and it's way easier to solve if you just think of it as 143. Now on the test, carry your decimals, but the distance that the 25th percentile is below the mean is the same distance that the top 25%, i.e. the 75th percentile, is above the mean, and we can solve like that. So really like these sorts of questions. They're very good to be able to find, stuff really quickly. Want other questions? Oh, there. Surely there's some more. Chapter 6, Chapter 4, Chapter 3, Chapter 2. We've had some people take the exam early, probably 15, 20 people, and I'm pretty happy with what's going on. I can't comment on anyone's grades. But from what I hear, people are saying, come to class. And I really mean this for the later exams. When it comes to exams 2 and 3, that is where it's like all new material. I think it's very hard to do well on the second and third exam if you don't come to class. Like, you're like, I'll just learn it the night before. Because this first exam has some easier stuff. But what do people want to cover here? It is your office hours. It's your time. So let me know what you want to cover. Question 6 on the practice exam. Yep. And do check out those videos. Are they loaded in yet? Yay, they loaded in. So if you go right here, there are the videos covering everything. Variable types, is that number 6? I'm going to mix them up a little bit. But there are the videos going over everything right here, all the concepts. So check that out. Here we go. Battery brands. Could you show us some chapter 6? Yeah, we do chapter 6 right after this. Oh, hey. And check out, let me put the timestamp on this. I'll sleep one of these nights. So stat 201. And let's go take a look. Definitely start early and ask questions whenever you're stuck on stuff. So let me know when you have questions. Okay, so here we go. The speedruns are amazing. Thank you so much right there. There's instances where you want P to be big and you want Good questions right there, Emma. Not necessarily that we want, but just that they are, and what does it mean? So, Emma, we'll review that next. We'll talk about p-values here and the tests we've learned so far. Want is a weird word in statistics because we don't really want anything. We just interpret what the results are. But I can see what you mean, like want. Like you might want normal data, or you might want to find correlation. In that instance, you want, but you try not to like be like, I want to see this. You just see it. You just find it. But no, I'm a good question right there. And you're saying how like there's different interpretations for different p-values. Yes, kind of. It always has the same interpretation, but means different things for different tests. More on that next. So, particular brand of battery. Tell me via the colors what these things mean. Okay, what are those values by their colors? Notation is going to be so important for later tests, especially test 3. So learn your notation now. Write it down if you don't have it. Tell me yellow is this, green is this, blue is this. It says under normal conditions. So it's talking about, well, it doesn't say it's, there we go. Under normal conditions. It's almost saying it's right here. So, more under normal conditions. It should say normal curve. Y is mu and theta. Oh, well, the y mu theta. Close. This is the y because that's the observed. And then this is the mean because it says average. And then this is the standard deviation, which is sigma. Whoops. 100 points. Brian made an error right there. So, and I think great job, Cameron, right there. I did make an error. That is mean right there. Mean is mu, like our channel Mewtwo. It's a Pokemon thing. And so when we want to find the z-square here, we know that z-square is equal to observation minus mean over standard deviation. So we put in the observed value of 2 minus 2.5 over the standard deviation of 0.32, which this is going to be a z-square of like negative, because it's below average. So let's go negative 1.6 or something. 2 minus 2.2. Oh my gosh. Thank you so much, Ty, right there. And Ty is correct. Negative 1.56. So what's the first thing you would think about if you get a question like this? Start whatting it. We should know when you get a question like this, start whatting it. We'll look at what the question asks here in a moment, but let's plot where we landed. So we're going to draw our normal curve. And we're going to put the z-score on it. 0, because that's the mean of the standard normal curve. We just found the z-score. And so negative 1.56. Z equals negative 1.56. That's where we landed, pretty close to there. And now it wants the percent of batteries that what? Last longer, right? So it says, what percent of batteries last longer than 2 years? Should I shade to the right or to the left? What way should I shade on this curve? Should I shade to the right of that point or to the left of it? Which way should I shade? To the right of it or to the left of it? To the right of it. So we want that area. Now we have a problem. It didn't land exactly on an empirical rule number. It didn't land exactly, good to see you here, Elijah. It didn't land exactly on an empirical rule number. But we could give boundaries to this. Let's think. If we were to shade from here over, would we shade too much or too little? If we were to shade from there over, would we shade too much or too little? Like, I'm just saying, we take this line right here and we only shade from here over. Would that, like, I go like this, I go, wee, and shade right there. Too little. I hate that it does that because it thinks I want to go to the cursors at. If we were to shade from here over, would we shade too much or would we shade too little? You see, from here over, we would shade too much. We'd have too much shaded on the curve. So that means the answer is going to be somewhere more than this area and somewhere less than this area. So we need to find two numbers here. So let's go ahead and try to find our two numbers by drawing on the curve. What percent of area is between -1 and 1? So it says use the empirical rule on this, I believe. It says there it goes, use the empirical rule. It says only use this. We bold it nowadays. What percent of area is between -1 and 1? 68. So that leaves 32% total outside, and that makes each of these worth 16. How much is above -1? How much is above -1? How much is above -1? 84%. Great job. So 84% is our too little. And I guess we need that percent there. And then how much is between -2 and 2? How much is there? And I'll do the outside trick here in a second. Between -2 and 2 is the next number on the empirical rule, which will be 95. And then if you've been practicing right here, you'll know that 5% is total outside, 2.5%. So how much is above this line right here? How much is above that line? Oh, 2.5. Where did I lose my 5 to? 97.5. So the answer is somewhere between 84 to 97.5%. Does that make sense? Really good question right here. Good practice on it to draw out the curve and figure out where we are currently at this current z-score. And then it has to be somewhere more than 84, but less than 97.5. And what we could do, and this is, we wouldn't have access to this on the test, but we could go right here and literally put in the observation on a curve with the following parameters. And then we could go to above 2, and there's the answer, which is very similar to our drawing. This is where you want to hopefully get to, where you could make a drawing like we have on the left there, and then be able to see the answer we gave is on the screen. So this is the kind of key learning objectives that if we had you draw pictures, you could then find the answer has to be between 84. You're confused. Which part are you confused on? So this is, we were able to narrow it down between somewhere between 84 to 97.5 because it had to be more than this, which is 84%. That's the two numbers added up right there, 68 plus 16. And then it had to be less than 97.5 because that's the area above -2. So, oh, because it wants the area above last 2 years or more. So because it wants the area above. Does that make sense? Below would be those numbers. Those are the areas below, but it said above. So that's where we were talking about at first. Do we want the area to the right of it or to the left of it? So you are correct. If you go below that, then the answer has to be between 2.5 and 16. And you could actually find that using an Applet picture, but the area above it is going to be this. These are the batteries that last longer than 2 years on this curve right here. Now we're showing the z-score. So if we do it with z-scores, we would have to put in the z-score of -5.625. And there's where it is on the curve there. And then these are the ones that are below it. Does that make sense, Martin, right there? How's that looking? Is it making sense? Like this is the same curve we have, but with the z-scores on here now. You see where I put this. It needs to be a little tiny bit more over, right about there. And there's where I put the line. So I drew the same line. Which part are you wondering about? Because we want the ones that take longer than this. So we found the z-score of it to begin with. We found the z-score of 2 years. So when we draw it on the standard normal curve, which has a mean of 0 and a standard deviation of 1, we'd get a z-score of -1.56, which I've drawn over here on the applet. And then we can use the empirical rule to break down the curves to say the area above -1 is 84%, hence where this number comes from, the addition of those numbers. And do you see where the 97.5 comes from? That's the area above -2. Tell me which part you're wondering about. Then we might do p-values next. And check out, I do it a different way in the video. Have you checked out the videos? Because the videos go over it in a different way. So sometimes hearing it a different way can really help. So check out the review videos. We've done some of the practice exam, but if you want to see the full practice exam, we got 2 more topics. I think people wanted correlation and p-values. If you want to go over any of the practice review test questions right here, I show graphics and stuff. Where is that one? Here's empirical rule question right here. And so this one right here, there we go. So I show this again right here, and I graph the areas, and I talk about the betweens. So definitely, have you checked these out, Martin? Because I go over, you're welcome. Yep. So check these out, because I try to make them really good with animations, showing you how we're getting these areas like I was drawing right there. And you get, Brian's not handwriting. You get the drawings showing you how we're getting these areas. And then you get And then I talk about why it's going to be 97.5 because we can find the area above there. And that's like we were drawing over here on our sheet of paper where we have the following, but it's just not as pretty right there. So check that out. We're going to talk some p-values here next. So let's do that section. Will the exam be formatted the same as practice exam with the multiple choice? It'll be like Canvas content. Good question there, Hayden. Good question. Yeah, it takes a while, Martin. It's in good questions. Martin, thank you so much. 50 points for being here and asking these questions. Anytime you have a question, let me know. I try to slow it down then. I know I talk quickly. P-values for correlation and normality. Okay, so we're doing p-values for correlation and normality. So this is a very advanced topic, which we make a little bit simpler for the first test. So when it comes to p-values, what does the p of p-value mean? How much time do we? You have 90 minutes. 90 minutes. What does the p of p-value mean? All p-values are whats? All p-values are probabilities. So we have 2 times that we've used this so far. The first time we did it, chapter 5, goodness of fit, checking normality. Okay, that's the first time we did it. Chapter 6, correlation, seeing if there is correlation. These are the 2 times we've done it. So be very careful right here. Stratify, we can do some sampling. You got it, Nick. So let's look at chapter 5 first. There are 3 ways to check for normality. Which of the ways can you name? And we'll get to the last way with the goodness of fit. Well, there's one of the answers. What are the 3 ways? And you can see one of them right here. What are the 3 ways to check normality? 3 ways to check normality. What are 3 ways? Way number 1 is just what right here? What are the 3 ways to check normality? The 3 ways to check normality are going to be what? What 3 ways do we have? Any ideas? I'm writing them out. Any ideas? Okay, here we go. Let's check them out. You ready? The first way to check normality of data is to just look at the histogram. Histograms that are normal are unimodal and symmetric. Just look at the histogram. Be like, yeah, that looks, I don't know, maybe it's got a little bit of left skew. Then we have a plot that tells us the probability it's normal, known as a what? A plot that tells us the probability it's normal. This is known as a what? A plot that tells us the probability it's normal. So I'm giving you hints with a plot that tells you the probability it's normal. Well, it is kind of a scatter plot, but this is the plot that tells us the probability it's normal, known as a what? And great answer, Jacqueline, right there. This is a normal probability plot. So that's the way to remember it. It's a normal probability plot. Now, do remember, dot plots are actually univariate quantitative. Well, yep. So this is a scatter plot technically. That is a right answer. It's not a dot plot, though, because dot plots are just histograms where we put dots instead. So this is called a normal probability plot. And why does this look normal? Just normal probability plot. Why does this look normal right here? Why would you say, yeah, that looks pretty normal? How do you know a normal probability plot is normal? How do you know a normal probability plot is normal? Close to the line, exactly. It's what we observe in the data versus what we would expect if normal. So it puts a line where they connect, like 50 and 50 match up. Like if the data is normal, 50 should be about here. Well, that's where we see the black dots. Now check this out. This data right here is definitely what? Oh my gosh, Photoshop opening. This data. This is going to go everywhere. This data right here is definitely what? This data right here is definitely what? Well, we wouldn't really say, there we go. This is a right skew monster man there. That is right skew. And so we don't look for linearity on a normal probability plot. Normal probability plots are only used for what? What is the only point of this plot, which was created for this histogram? This histogram right here has that plot created for it. What is the only point of a normal probability plot? It's not to check for linearity, because a lot of people will see that and be like, oh, it's linear. So good answers, Rachel, there. We don't check for linearity with it. The only point to a normal probability plot is to check what? The only point to a normal probability plot is to check what? Kind of, we could say that, but think it's called a normal probability plot. So the point of it, kind of, Martin, we'll think it's called a normal probability plot, is to check to see if it's normal. So if it fits the normal, it follows the line. If it doesn't fit the normal, it doesn't follow the line. So when we look at this, we're trying to say, is this normal? And the conclusion for this histogram on the left with its associated plot, like this, these are the same data making this. So what would you conclude from this normal probability plot? You wouldn't include not linear, or you wouldn't talk about the linearity of it, since these points deviate from the expected normal relationship or the normal values of what we would expect. You would conclude what via this normal probability plot right here. So this is its associated histogram. Like this is the same data. You would conclude not normal. Great job, Rachel, right there. So the normal probability plot is kind of a way we look at it. Is it probably normal? This one is the answer no, where this previous one we did over here, I'll take a screenshot of it so you can see them both at the same time. This one looks pretty darn normal. So the normal probability plot will do what mostly? So this one looks pretty normal. So when we make it into a normal probability plot, the data will do what now? So normal probability plots where the data is normal generally does what? Well, generally, it's right over here. So this is the data, and this is its associated plot. When the data is normal, it will follow, it'll fit the line exactly. And it's not like there's a linear relationship. It's just that the values we see, we would expect if normal, are the observed values, and they match up right here. So it's basically matching what we would expect given normal. That's a way to talk about it. We could just say they follow the line right there. They fit the line. That would be acceptable right there. But there's the last thing I have right here, which is called a Shapiro-Wilk test or a goodness of fit test. Now, the way a goodness of fit test works is we take the histogram and we see if the normal curve is a good what on it. So we take the histogram and we see if the normal curve is a good what. We take the histogram and we see if the normal curve is called a goodness of fit test. We see if it's a good fit. Now, the exact way to memorize this for this test is low p-value indicates non-normality. Low is less than 0.05. High p-value, dash over here. High p-value indicates normal, or we can say lack of evidence of non-normality. So high is greater than or equal to 0.05. Okay. So when we look at this right here, we've got the original data right here, and tell me, do you expect the p-value to be high or low on this test? So if there's a low p-value, that is evidence, or we should say evidence non-normality. And we would have lack of evidence. So I'm going to put indicates normal because the technical terminology would be lack of evidence of non-normality. I just want to speak more normal to for the moment, where a high p-value would have you believe that it's still normal. But in the technical sense, we lack evidence of non-normality for those statisticians listening in. The p-value is going to be high, right? We would think. Let's hope it follows what we should think. And there you go. There's the p-value telling us that it is likely that this came from a normal. Going into a little more advanced statistics for a half second, the null hypothesis is normality on this. A few people know some more advanced. We keep it a little bit simpler to start, but we would not reject the null hypothesis of normality because we do not have enough evidence to reject it. Thus, we would continue to believe that this is normal, i.e. we continue to believe the null hypothesis of normality. We lack evidence to show that it is not normal. But we're just saying, it's probably normal. The data, assuming it's normal, what we saw was likely. I think it's normal is the whole point. Now we look at this one right here, and this p-value is going to look weird for a second, but that p-value right there is actually this. This p-value right here is very, very what? Got it on the dot. That p-value right here, which is in scientific notation, is extremely what? And it came from this data right here. And so think about that and use the notes on the screen to help you out with these p-values. So that p-value is extremely low, right? So you would say what? You could say, I have evidence what? Which, I mean, you could look at this and say, I have evidence what? Low p-value, so we have evidence not normal. So this is, or you would just say not normal. Like it's evidence that did not come from the normal. And that would be the exact statistical talk would be, I reject the null hypothesis that it's normal. I have evidence or very strong evidence of non-normality. Just look at the histogram, or rather look at the test. It's very unlikely we would get these data points given it came from a normal. So a high p-value for normality on histograms and low p-value, wait, careful. So Hayden, we're going to the next one. And Hayden, great job right here. That's where we're going to go right here and do correlation next. So these are the notes when testing normality. So to be very specific, Hayden, each test kind of comes to the idea of a p-value is below 0.05 is statistically significant, which means unlikely by random chance. But the key to each test is, what are we testing for? In this test, we're testing for evidence of non-normality. Does that make sense? We're testing for evidence of non-normality. We'll put that here at the start. Tests for evidence of non-normality. I hope this kind of connects all the dots. Tests for evidence of non-normality. And a low p-value is evidence for non-normality. But think about this. When we test for correlation, what are we testing for? If you test for correlation, you'd be testing for what? So we're going to kind of build this knowledge right here and be like, okay, in chapter 6, we use a p-value to test if there's evidence for what? So what do you think we would test to see if there's evidence of? What do you think we would test to see if there's evidence of? In chapter 6, we would test to see if there's evidence of what? Give it like 10 more seconds. Don't worry if you get it wrong, because you're probably between two answers. Kind of, Hayden, kind of. I mean, it's basically the gist of it. More simply put, testing for evidence of correlation. We're going to test for evidence of correlation, which is a linear, Pearson is a correlation of linear relationship between X and Y. So when we do this right here, we can take the same sort of notes we have and do low p-value is evidence of correlation. You see how it works? So we can just say it's evidence of correlation. Indicates, what would a high p-value indicate to us? So think if low p-values in chapter 6 are evidence of correlation, what do you think a high p-value would be? And don't go too in depth, just be like, oh, if a low p-value is evidence of correlation, you could say, we should probably say this. Or not enough. Yeah, there's not enough evidence. Does this make sense here, Hayden and Nick and everyone listening in right now? And also I saw, where was it? Where are they at? They replied. Why don't I see it? Great job, everyone listening. Does this make sense? A low p-value is going to be evidence of correlation, and a high p-value is going to mean we don't have enough evidence. Like we didn't. Great job, Doc, right there. So let's run this right here and take a look. So I want you to think about the way this looks. Just look at this plot. You ready? Here's X. Oh my gosh. I like using R because I can generate data so quickly. I don't have to type it in. Oh, what? Oh, 2 R's. Okay. Guess the correlation of this graphic. Guess the correlation of that. Guess the correlation of this plot. Would be a decent problem on the test. 0. 0. So now think about the p-value. When we talk about p-values, a low p-value is evidence of correlation, and a high p-value means we do not have enough evidence for correlation. So if you had to guess the p-value of this, what would you guess the p-value of it to be? Which is the likelihood of getting this result, given there is no correlation, technically the null hypothesis. So will the p-value be high or low? So low p-value is evidence of correlation, and a high p-value is the lack of evidence of correlation, not enough evidence. So let's go ahead and run it right here. Core.test. That's how we run it over here. So this is another hypothesis test right here. We're going to go x comma y. And there's the value of the correlation. We said it'd be close to 0 because it looks really random. And the p-value is actually very close to 1. And what that means here is if there's no correlation, seeing something like this is very, very what? If there's no correlation, an observed plot like this, think about that high of a probability. If there is no correlation in the data, so because we're looking for evidence of correlation, but if there is no correlation, seeing something like this is very, very what? So what does a very high probability mean? Think of an L word. Very, very high probability would mean that what we saw here seems very what if there's no correlation, which is a proper interpretation of the p-value, that 96.12% of the time a result like this would occur given there's no correlation. Not linear, likely. Good guess right there, Rachel. We'll give you 50 points for the guess. Likely. That's what p-values are. They're probabilities, saying that this is a very likely result given there's no correlation. So think about this, though. What about this relationship right here? This relationship right here. Take a look at this. Does that look to have a linear correlation? If you had to guess the linear correlation on this, what would you guess? If you had to guess the linear correlation on this, what would you guess? I wonder if you can get closer to me than I can. Ooh, let's see. I'm going to give 100 points if Amelia beat me. I'm just going to say 0.96. Let's see. I say 0.96. Amelia, that's a really good guess. Oh, it's even, who said, did someone say Amelia was closer? It's super duper strong. So Amelia was closer. The correlation is 0.995. So this is very, very strong. And look at the p-value. The p-value is very, very what? 1 less 0. The p-value is very, very, oh my gosh. The p-value is very, very what? And that is the p-value out of scientific notation. The p-value is very, very what? So we tested for correlation, and the p-value is very, very what? Very, very low. So how would you, if you had to interpret this to somebody, you would say we have what for correlation? What would you say we have for correlation? Remember, this is a test for correlation. Don't confuse it with the previous test we just did for chapter 5 to test for non-normality. You would say I have a lot of what here with this plot? I have a lot of what with my data right here? A very strong evidence of correlation. And you would say what you saw here is very what, given there is no correlation. Think about what the p-value means as like interpreting it. If there is no correlation, a result like this is very what by random chance. The observed result right here is very what by random chance if there is no correlation. And yeah, very strong. It's very unlikely. Yes, you're getting it, Rachel. Great job right there. This is a very unlikely result. Take that back to the previous one where this was a likely result. That's not the result. This one was a likely result by random chance if there's no correlation. And this one is an unlikely result over here. Now think about the previous example. I'm going to bring it together here. If the data is normal, this is a what result? If the data is normal, like let's assume the data is normal, this result over here is what by random chance? If our data is normal, this result over here is a what result? Because we're assuming it's normal to begin with. Would this be unlikely? Wait, this right here. This is unlikely to see? If the data is normal, this is unlikely? If the data is normal, the p-value is telling us this is a what result? This is likely. But if the data is normal, this result over here is very, very what? And once again, this is the p-value. If the data is normal, this result on the right is a very, very what result to see? Unlikely. So you'd be like, yeah, I don't think that's really likely if it's normal. I have evidence it's not normal. This has been a much more in-depth talk on both of these interpretations. The test really doesn't go that extreme on it. If you get a low p-value, that means what you saw was what by random chance. For this test, be careful. That's only for this test. Remember, we did both tests. So don't always think high p-value means normal. It's, to be very exact, on the test of normality, a high p-value would mean that we did not have evidence of non-normality. So no evidence of, or not enough. So that's more exact, like very like the high p-value would mean we did not have enough evidence to conclude it's not normal. So we don't know that it's normal. We just didn't find evidence. That's how we like to talk, because we look for something like, oh, we didn't find evidence of that. So yeah. But remember, high p-value always means what? What could you always say about a high p-value above 0.05? So all high p-values above 0.05 or higher are not what? All high p-values above 0.05 or higher are not what? So I'm going to round off all your knowledge on this that we could basically possibly ask you. All high p-values 0.05 or higher are not what? There's a key phrase. We say, like, when they're below 0.05, they're this. All high p-values above 0.05 or higher are not statistically significant. So, but no, these would be likely. So these are, and good work, Michaela, right there. These are the likely ones because high probability likely. So statistical significance, p-value less than 0.05 means our results are unlikely by random chance given the null is true. And the two we learned were normal and no correlation. I know it's weird that it's no correlation, but that's the null hypothesis. We're looking for evidence of correlation, so we assume there's no correlation until we have evidence of correlation. P-value below 0.05, evidence of correlation, correct. And that is when we test for correlation. So make sure to, so we have the two different things right here. We took a lot of notes, basically did a little review of both of these chapters, but that's the in-depth, probably, what do we do, 20, 30 minutes on this? But that's, do people feel like they understand it better? This was 25 minutes, all about the p-values and the two different tests we have to check for normality or to check for correlation. There are some of the more advanced things I would say on the test, but if you start to understand this now, you'll understand it for test 3, which is really where we use them. People want to do some stratified and cluster, so let's do that. Okay. You're welcome, Jacqueline. Great job. Okay. Oops, didn't label that. Okay. Stat tool 1, sampling methods. Thank you, Rachel. That's our goal. So when it comes to sampling, have your note cards out. Be able to do this. Like, try doing multiple versions of this. Take your note cards, write the definition of it. I know hearing me is great, or like you'll learn it a little bit, but you want to write down the definition of it and put the name of it on the back, and then do other note cards where you do examples and then put what it is on the back. Then you'll remember a few, and you might even do some we do on the test. You never know what you'll think about. Okay, so the 4 types of sampling are, we have here simple random sample, we have here systematic, we have here stratified, and we have here cluster sample. Can anyone tell me about any of these right here? It really comes down to memorization with these and practice, where you just go over the definitions multiple times and you're like, I know it. You want to be able to memorize these, have them down, and be able to give examples of them. It's one thing to memorize, but it's another thing to be able to come up with your own examples, because then, you know, you just look at the test and be like, what example is like that I came up with? So simple random sample. Everything in the population gets a number, then we select randomly the observation. Everything has an equal chance to be selected. So with simple random sample right here, nice multi-stage, putting together different types. So multi-stage can be pretty anything. So simple random sample, if you go to the registrar and you say, select for me 50 students, and they randomly generate a list of random students for you, that would be a simple random sample from the registrar of UTK students. You could just have names in a hat and pull out like 10 names. If you had everyone's name in the hat, that'd be a simple random sample of the people in the room, and you'd be, sampling from everyone, giving them equal and likely probability of being selected. Although we say give everyone a number, the idea is still that you just have access to everyone and you randomly draw names, and that's a simple random sample. Stratifying is when we acknowledge difference in population, and then we put, yes, that is stratified. Stratified is one of the tougher ones, so let's talk about that. Stratified, you need to acknowledge a difference that you are sampling with respect to. So think about this. If I'm going to go to UTK students and ask them, who are you voting for the next election? And Brian goes to name Democrats, Republicans, Green, Libertarians, name a group real quick. You are picking the example. Name Democrats, Republicans, Green, Libertarian, name someone. I'm going with the first name people drop in the chat. Democrats, Republicans, Greens, Libertarians. I guess stump me with like a group I don't know. Need someone to pick the way the example goes. That way I'm not biased. It's a random poll. So I'm going to name a political Donald Duck Republican. So, Republicans right now, we got, I can't think of the Florida name. Why can't I think of it as Ron DeSantis? We got Trump and DeSantis, Cruz. I don't know. Cruz is running, is he? I don't know. I'm not trying to. Ron DeSantis in Florida. We got Trump running, maybe a few others. And so all of a sudden I come out here and I say like, wow, UTK students are majorly in favor of these candidates. Like everyone's saying they're going to vote for them. What would you say to me about if I went to the college Republicans and talked to them and tried to understand UTK students? What would you say right there? What would you say to me if I was like, wow, UTK students are like Donald Trump, Ron DeSantis, Ted Cruz? Oh, we can talk about that here. Mm-hmm. What would you say to me? If I was like, wow, like everyone's voting for those candidates. It's biased, right? We actually have a problem right there called undercoverage. So we undercovered the political affiliations of different students. So you'd say to me, Brian, we did some research and we found out that UTK is 25% Democrat. We are in the South. And 50% Republican. And 25% other. Just fake numbers right here. So now, when I sample to understand UTK students, if I sample 200 students, how should I do it? And this is what stratifying is. You're acknowledging a difference in the population, and then you are going to sample with respect to those differences. So what should my 200 sample size look like? So the population of UT looks the following way. The population of UT looks the following way. How should my sample look? If I sample 200 students, I should do what then? How should my sample of 200 look? Who can start me out on your sample of 200 would look how? And this is key because we want it to look like the population. Because we know people's views on who they're voting for might differ by their political affiliation. So how would we sample the 200? And so what would that... So EC is correct right there. Great job, EC. Because we would go right here and we would say 50 from this, 100 from this. And what if someone said to me, Brian, you sampled more Republicans than Democrats? What would I say to that person? Because I sampled 50 Democrats, 100 Republicans, and 50 from other affiliations like Green, Libertarian, I don't know, whatever other parties. I'm so bad at naming them. But if someone said, Brian, you sampled more Republicans, what would I say to them? I would say, well, UT has this makeup to properly represent the population. My sample has been stratified, acknowledging a difference within that you are sampling on to make your sample look like your population. So now, although we have more Republicans, that's just the way the population is, and then our sample mimics the population. So stratifying is meant to acknowledge a difference. Now, and so we then randomly sample. It's not multi-stage here. We would then randomly sample within the strata. So each one of those is called a strata. Strata is layers in Latin. But cluster sample is usually where people get confused. Because if we did a cluster sample on ideology, what would we do? Cluster samples are things in the population are put into groups randomly. We then take these random clusters and do a census on a few of them via simple random sample. How would one normally decide? Usually, sometimes they might do a pilot study or something like that, or they might have ideas of the demographics. So that's usually what a researcher will do. They'll say, like, from the census or something, we know that America's made up this way. So, or this area, this town has this sort of demographic. We think that this is an important characteristic to stratify on. And so we could do that, Hayden, right there. That is a good example of cluster sampling. But if we did a cluster sample up here, like, let's do bad sampling. What if Brian considers ideology, political ideology, to be something he can cluster sample on? So what if someone said political ideology is something we can cluster sample on? What would you end up doing? So I want you to think about why this would not be a good sampling method and it doesn't meet the idea of cluster sampling. So what would you be doing if you did political ideology as the clusters, not as strata? So why would this be bad right here and would lead to really not good results? Like, you wouldn't understand your population. So in cluster, things in the population are put into groups randomly. We then take these random clusters and do a census on a few of them, or one of them. It depends on how big the clusters are. And we want them to be, the clusters, yeah, they should be similar between, right, Hayden? And so if you did a cluster sample, you would basically go here and do what? Take what and do a census on them. How many, if Republicans was the cluster, how many people in that cluster would you speak to, Hayden? I think you're seeing it. If Republicans was the cluster, how many people would you be speaking to in the Republican cluster? All of them. So is that representative of UT to go to like all Republicans and talk to all Republicans? No, they're not randomly assigned to that cluster. So cluster sampling is really meant to speed up the process. I like to think of bags of M&Ms, which we talk about a lot. But if you were to go here and say, to understand freshmen at UT, 3 different orientation groups, or incoming freshmen at UT, 3 different orientation groups were met with and given a 30-minute survey on their experience of the campus. Would this help us understand most incoming freshmen? You could talk about we could talk about undercoverage. Would this be a decent way of doing it? Would this be a decent way of doing it? Would this be a decent way of doing it? To understand freshmen at UT, 3 different orientation groups were met with and given a 30-minute survey on their experience of the campus. Would this help us understand most incoming freshmen? What are your thoughts? I would say this would be pretty good, right? Now, you could say some people don't go to orientation. Yeah, that's the problem, is like we probably have some people who don't go. So, it's going to be tough. Those are going to be the people who kind of maybe give us non-response or we have under coverage on. So it's going to be hard to get an exact, feel for everybody. But if we chose 3 different orientation groups and spoke to them, got their experiences, we could probably understand, at least we could say we understand the people who come to orientation. So would this help us understand the views of the 50 orientation groups? Do you think this would be a good way to understand the view of the 50 orientation groups? Now we've kind of limited the scope of this. Well, the thing is we want to make sure that each orientation group is pretty much a random selection of students. It's not like one orientation group is in-state, out-of-state, like, oh, this is the out-of-state orientation, because then we would need to stratify on that difference right there and say we need 2 in-state groups, and 1 out-of-state group. So it really depends right here. So when you take a whole orientation group, how many of them are you going to speak to when you do a census on the orientation group? So if you take a whole orientation group, you would be doing a what on the group right there? What would you be doing? You're speaking to all of them. So you'd be doing a census. You'd be speaking to everyone in the orientation group. We didn't do systematic. Systematic's the easy one, or one of the easy ones. Easier, I should say. So pick a random starting point and sample every kth observation from here out. So I could stand outside the library and talk to every 10th student who walks by. Would you say that cluster sample is least commonly used for random samples? No, people take like groups, like you go up to a table and talk to everybody. You could just be doing clusters of people right there. Clustering helps speed things up. Like clustering is meant to be like, instead of me just getting one observation at a time, I can just grab 20 observations right here. But the 20 observations need to be randomly put together. If you're going to speak to an orientation group, you are assuming that the orientation group is just a random group of students that are the ones you want to understand. So would the orientation groups be a good way to understand all UTK students? Would this help us understand the needs of all people at UT? So now you have to think, would this clustering scheme be good to help us understand all people at UT? So we're going to go to the, whatchamacallit, freshman orientations. Would this help us understand all people at? No. Now we're talking like faculty and staff and everyone at UT. Not everyone at UT is an incoming freshman. So if we were to properly say here, would this help us understand the views of the 50 orientation groups? Probably. And so if you did a simple random sample, how would you do a simple random sample of the 50 orientation groups? So if you had to do a simple random sample, which you could do, you'd have to do what? You'd have to give everybody numbers, and then you would randomly select people from the 50 orientation groups. So everyone in the 50 orientation groups would have an equal and likely chance to be selected. But if you did a cluster sample, you'd have the 50 orientation groups, and you would select 3 of the 50 clusters. So we could say, okay, sample from 1 to 50, 3 observations. We're talking to, I did not do that. Oh, I did sample, not sample. We're talking to cluster 41 or 44, 31, and 40. So those would be the 3 orientation groups we take as our clusters, and we speak to everyone within them. Multi-stage could be like if we have in-state and out-of-state orientations, we take like 3 in-state orientations and 2 out-of-state orientations, because now I'm doing a cluster by taking all the people at those orientations. And what am I doing that makes it stratified? By saying, so this is a multi-stage now. I could say, take 3 orientation groups from in-state and 2 orientation groups of out-of-state students. So the orientation groups themselves are the clusters, but why is this now stratifying? Why is this now stratifying? Why is this now stratifying? So it's a multi-stage because we're doing clusters by taking the orientation groups, but then we've added an element of stratification right here because now we're not just taking random clusters, we're making sure we take 3 clusters from here and 2 clusters from here. And so the stratification is the acknowledgement of the difference. So we're acknowledging a difference right here. The 3 in-state and the 2 out-of-state is a difference. Like in-state and out-of-state students, incoming freshmen, would be inherently different right here. So we're saying, okay, the differences in the groups are the stratification. The taking of a whole group is the cluster right here. So why do you think I'm choosing 3 in-state? Like, what have I kind of maybe assumed about this population? Why do you think I'm choosing 3 in-state? Why wouldn't I just choose 2 in-state, 2 out-of-state? I'm like, no, we really need more like 3 in-state. Maybe we could do like 4-2 or 3-2. We'll talk about that and we'll decide upon that. But right now I'm decided on doing 3 in-state. There's more in-state students. So we know if we're going to get the views of the orientation groups, we have more in-state students who come. So maybe it's like a 60-40 split. And that way I'm going to speak to 3 of the in-state groups and 2 of the out-of-state groups. You might say, but that's you taking less. I say, well, yeah, that's with respect to the percentages in the population. We then take the amount. Now, usually with stratified, you just do a simple random sample. That doesn't make it multi-stage. You have to get them somehow. So usually just simple random sample within the strata. Your clusters are selected via simple random sample. Doesn't make it multi-stage. You just have to somehow get those values. Any questions on these? Right, we might take a short break and I might grab some lunch. But these are the sampling methods. Oh, we had versus. We had sample. We have sample. Boop. Sample. Statistic. Population. Parameter. Okay. So I like to say SSPP because sample statistics give us inferences into population parameters. A sample, the group we collect data on. A statistic is a value we learn from the sample. So when you get a statistic, it's like you play 10 basketball games and your statistic would be kind of your free throw percentage. So you would take a sample of your 10 games and then you'd get a statistic right here. Now, a population is everything we want to understand. So if the registrar tells you they have data on all UTK students, that's going to be the population they have data on. So they have everyone right there. They have all UTK students. So when the registrar tells you the GPA of students at UT, they're actually telling you a parameter, the true value for the population. So a parameter is just like a what? A parameter, but it's not for a sample. A parameter is just like a what? A parameter is just like a what? Like the parameter of interest. We call it of interest sometimes, or population of interest. Keyword being parameter or population. The parameter is just like a what? Because it's a value. The parameter is just like a what? What is the parameter like? The parameter is very similar in idea. Well, the sample size is how many we speak to. It's similar to a statistic. But the difference is the parameter is what is true for everybody. So if you have a sample size of, let's say, 200 students, and you learn the GPA of 200 students, you have just learned a what from a what. So if you go out and talk to 200 students, you have just learned, and you learned their average GPA is equal to 3.6. You have just learned a what for the what. You now have a what for the what. Go into more detail. You have learned a blank. You have learned a statistic from a sample, right? Perfect answer, Rachel, right there. You've learned a statistic from a sample and a sample size of 200 right there. Now, the population of UTK students is something like 30,000. The registrar has this information, and the registrar would also know the true mean. So the registrar knows the true mean. The registrar knows the what for the what. The registrar knows the true mean for all students. So that's a population size right there of 30,000. The registrar knows the what for the what. The parameter for the population. Exactly. Does that, so I hope this makes a lot more sense right here doing these examples. They know the true value for the population, which is the parameter of interest. And that's the thing. We call it of interest, just meaning what we want to know. Sometimes people really try to confuse you with population parameter of interest. That's just what we want to know about a population. So you were interested in understanding it. So you took a sample and your statistic is your best estimate. So we can say the best estimate of the truth. There's a best estimate of the truth. So estimate of truth. We're down here. This is the true value. So you might estimate that the GPA is 3.6 in truth. And this is what the mean is. The mean is the true value for the population. It is 3.72. And if we had a standard deviation, which came from a sample, this is what I love about doing data analytics. Because if you had your sample standard deviation of like 0.5, you could actually go over here. We need to generate it, right? Well, darn it. Random normal times random normal. 200 observations. Mean equals to 3.7. and then standard deviation of 0.5. There we go. And let's store here values. And then let's go here to t.test of values. And there's the interval to estimate the truth. And that's how quickly we can do, oh, it's 3.6. I'm simulating the example. There it is. And we would have not had the truth in there. Maybe our sample was biased. Dun, dun, dun. So that's how we can quickly kind of do data analytics with things in R and do a simulation of a random, assuming it's normal, normal data right there with a mean of 3.6 and standard deviation of 0.5 and 200 observations. And yeah, so there was a sample size of 200, sample mean, sample standard deviation, and the truth was not contained to that interval. You know, sometimes it's not. What other, well, we'll finish up right here, but great job, everybody. I think we marked this right here. Did we? We did sampling methods. Yep, sampling methods. That was the last. Wow, we did that for a good 20 minutes right there, but we'll be back with class today. Good job, everyone, and great job learning. You're welcome, Rachel. Come with more questions. Like, I appreciate it so much. Like, I mean that in a good way. Keep coming with those questions. That's what I mean to say. Like, I'm not be like, bring more questions, but always bring those questions. Always let me know what you're thinking. And great job, everybody. I'm going to go grab some lunch, and I'll see everyone for class. Bye for now. Bye. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.